Okay, let's look at refraction and something that is called total internal reflection. Total internal reflection. TIR. Okay, so total internal reflection. So all of the light is reflected internally. So we have some sort of situation here where we have excuse me, some N inside and some N outside. So two different materials that have different indices of refraction, and there's somehow the light has gotten in. So maybe it came from out here and got in, and so it's going to hit the surface, and some of it is going to reflect right back in off of the surface, and some of it's going to refract and bend and be on the outside, right? And so when we have small angles, small to the normal, then it bends on the outside, and if N on the outside is smaller than N on the inside, then the angle on the outside is bigger. All right, so as you keep getting bigger and bigger angles, you're going to get to a point like this red line where the light hits, and then the angle on the outside gets to be 90 degrees. All right, so that's what we call the critical angle, because now it stays on the inside. Right, whereas before it would bend and be out here. Now, if we go a little bit bigger like the blue, then it's totally inside, purple even more inside, and so it's reflecting inside. It's totally reflected inside, total internal reflection. And so when does that happen? It happens according to this equation. And so basically we're just doing N1 sine, or N in sine theta in equals N out sine theta out. The theta out becomes 90 degrees, so sine theta out just becomes 1, and so we get sine theta in equals N out over N in, and so then theta in, which is theta critical, the critical angle, the smallest angle inside that will make it be 90 degrees or more, basically, or it's the angle that causes it to be 90, and then everything bigger than that will stay inside. So theta critical is then sine inverse N out over N in, like I have up there. Okay. So if we have something that has a smaller theta c, means it has a bigger index of refraction, right? Bigger index of refraction makes this fraction smaller, makes theta smaller. So diamond, for example, has probably the biggest index of refraction, anyway, a very large index of refraction, and so that's why they're all sparkly, right? Because most of the light that gets in and starts bouncing around stays in. It doesn't go out the other side. So let's just go ahead and find theta critical for these different things. So we got for diamond, for glass, and for cubic zirconia. Okay, and so theta critical for diamond is just plug and chug here. So we get inverse sine of, let's say we're in air, so we'll just say N outside is equal to 1. All right, and so then N inside is N for diamond, which is 2.4, and so we get, come on, inverse sine of 1 divided by 2.4. So we get 25 or 24.6. Theta critical for diamond. Right, how about for glass? This is going to be the same formula, sine inverse 1 over 1.5. Anyway, type it over. Sine inverse 1 divided by 1.5. That one is 41.8 degrees. All right, so if it comes in straight, some of it's going to get through, or a lot more of it's going to get through for steeper angles hitting the back side of the glass. So it has to be all the way to 41 before it all stays inside. And cubic zirconia, they're pretty sparkly. Sine inverse of 1 over 2.2. Let's see if I can get this formula to come back. There we go. 27.0 degrees. All right, so again, the bigger the index of refraction, the smaller the angle, the critical angle, the more light will bounce around inside. We can play with some lasers in lab and shine them on some diamonds and see how sparkly they are, see the reflections. And also diamonds are cut so that they have a lot of sides that will reflect as well to keep that angle, keep the angles large so that it can keep reflecting. Okay, let's look at part D here. And so we're going to do dispersion. Dispersion is when light, different colors of light bend different amounts, and so we can get rainbows, right? And so dispersion happens because N, index of refraction, for some certain material can be different, or is often different, for different wavelengths of light. So red light will have a smaller index of refraction, right, because it's got a longer wavelength. All right, so kind of here is the picture. So red has a smaller N, it has a longer wavelength, it moves faster in a material, versus blue or violet, they move slower, they have a shorter wavelength, they have a bigger index of refraction, bigger N. All right, and so when white light comes in that's made up of all the different colors, the violet will bend the most, the violet will bend the most, will have the smallest angle inside to the normal, so it bends the most, whereas red will bend the least because it has the, let's write this out. So N1 sine theta 1 equals N2 sine theta 2, Snell's law, right? And so if they all have the same, they're all coming in at this 30-degree angle, for example, then if something has a bigger index of refraction, right, if the blue or the purple has a bigger N, then to balance out to be the same, the sine theta, the theta itself, is going to have to be smaller, all right? And so that makes it closer to this perpendicular, right, which means it bent more. Vice versa, if N2 for the red is smaller, then the angle better be bigger, because multiplying together you get the same number as, you know, the stuff on this side, and so then that angle theta red is bigger, means it bends less. It kind of stays more in line with what came in, right? If N was 1 on the inside, then it would stay straight in line, but it's not 1. Okay, so let's find theta 2. So we're first so a prism also has this nice, we'll say it's a triangular shape, but let's say it's an equilateral triangle with all three sides the same, all three angles the same, and so that also helps separate. So we separate once at this interface, and then it gets even more so due to the angles and to the indices of refraction on the other side. So first off, let's find theta 2. So theta 2 are just these two angles from the first bending, first refraction. So theta 2, well, let's write out the Snell's law like we have here. So N1 sine theta 1, they're all together here, is going to be N2 for red sine theta 2 for red. All right, and so we can put in numbers and solve this, or just solve it algebraically. Well, let's go ahead and put in numbers. So we're saying N1 is out here, N1 is 1, or N is 1 for air. So we're going to say 1 sine of 30 degrees was our theta 1 equals N2 R. So N2, 2 is on the inside, so that's the 1.3 for R, sine theta R, theta 2R. All right, so we can divide through by the 1.3 and take the sine inverse. So sine inverse of 1 over 1.3 times sine 30 is theta 2r. I guess it is. Equals theta 2 red. All right, divide through by the 1.3, so that gets underneath, and then take sine inverse to get to theta 2r being by itself. And so we will do sine inverse of, we better put it in parentheses, 1 divided by 1.3, close those parentheses, and then multiply by sine of 30. So we get 22.6 degrees. Okay, so this angle in here from the normal, from the perpendicular, is 22.6 for red. We'll have the same, very much the same kind of thing for blue, or violet, I guess we're calling it violet. So n1 sine theta 1, still at 1 sine 30. N2 for violet, though, N2 violet sine theta 2 for violet. N2 for violet we said was 1.5. And these are just made up numbers. I don't know if any glass really does this, but we'll just go with it. And so rearranging for sine theta 2v, sine inverse 1 over 1.5 sine 30. So theta 2 for violet. Do a little cheating, grab that same formula, but divide by 1.5 instead of 1.3, and we get 19.5 degrees. Alright, so this one's only 19.5, whereas that one was 22.6. So this may be a bit exaggerated difference in index of refraction, so we get a couple degrees difference between the two. Okay, so that's that interface. Now what about when it comes out here? So this is what we would see on the outside, hopefully making a rainbow. And remember, the other colors are in between, so blue would be somewhere in between, and green in between, yellow, orange are all in between there to make the whole rainbow. So we're just kind of doing the outside edges. Okay, so we want to get theta 3. Okay, so theta 3 is on the inside here. We're going to use Snell's law then to get theta 4 on the outside, but first we've got to get the angle inside here. So each one of these is going to hit this outside of the prism. And so now N2 is these ends for glass, and then N3 is going to be back to N1, is going to be back to air, okay, when we write Snell's law again. But first off, we got to do some triangle work here. So we want to know this angle in here. How can we get that angle? Well, we know it's going to be a bit of a mess. Okay, we know theta 2, for example, for the red. Theta 2 is, let's just do whole numbers here. Let's just do 23 degrees, and let's just call this one, it was actually 19.4 something, so let's call this 19 degrees. Okay, and so doing the red, this one is 19 degrees, or I'm sorry, this one is 23 degrees. 23 degrees in here. This whole thing is a right angle, right? And so this is 90, and then 23 of it is here, so that makes this be 90 minus 23, 67 degrees. All right, and so this, from the red to here, 67. Now we have a triangle here. For a triangle, the whole thing is 180, right? All three angles added together. And so this angle is going to be 180 minus 60 minus 67, right? Because the whole thing's 180, subtract off this, whatever's left is this guy. So 180 minus 60 minus 67. So this angle is 53 degrees. Okay, we're almost there. So now theta 3r, let's see, this is part E. Theta 3r is in here. So together with this 53 degrees, it makes 90, right? So theta 3r is 90 minus the 53, right? Whatever's left from taking the 53 out of the 90, that's what theta r is. So 90 minus 53, 37 degrees. Trig is good. Okay. Theta 3 for the violet. Whoops, sorry, I'm getting off the page. Theta 3 for the violet. That same kind of thing going on here. So now we need, let's redraw this a little bit here. So we've got the perpendicular and the violet is going something like this. We still have 60 here. We have this angle here is 19 degrees. This whole thing is 90. So this angle is going to be 90 minus this part that's 19. So 90 minus 19. So now this one is 71. Okay? This triangle. And then we were going to have the refracted ray coming out of this. So I'm trying to draw this kind of triangle here. The one that's got the top of the prism and then the purple line. All right, so 71 there. And then we need this one so that we can get, we're really looking for this one right here. This is theta 3v, but let's find this one because it's in the triangle, right? And so we got 180 minus 60 minus 71 makes this angle, because this whole triangle makes 180. Got these two that we know, so we could do 180 minus 60 minus 71, 49. So in here is 49. So theta v, 3v is, well, theta 3v plus this 49 makes 90, right? So theta 3v is 90 minus 49. Okay, trig, a little bit of trig, triangles and right angle stuff. Okay, so for F then we can finally get the angle coming out here. So what is theta 4r and theta 4v? So theta 4r, let's write the whole thing out. So we got n 3r sine theta 3r equals n 4r sine theta 4r. So just going in here with the 3, out with the 4. n 3r, we're inside the stuff, so that's going to be 1.3 from before here. And 4r, the 4's are back out in the air, so it's air, so it's 1. And we just got to say theta 3r is 37 degrees. And so theta 4r is sine inverse of, divide through by 1 this time. And so it kind of goes away, but we can put 1.3 over 1 times the sine of 37. No, not that. I didn't mean it. Sine inverse of 1.3 times sine of 37. 51. Let's just do 51 degrees. Is theta 4r. Alright, here we would expect this one to be even bigger. Theta 4v is going to be the same formula except for there are going to be v's everywhere, and so it's going to be sine inverse of 1.5 for the nv over n1 is still 1, sine of, instead of 37 we're going to use the 41. So inverse sine of 1.5 times sine 41. Right, so the first refraction made these angles different, made this one bigger, so it bent more, and now this index of refraction is going to make it bend even more for this one, so we get 70, well, 80 actually, degrees for theta for V. Alright, so this is, it kind of looks like that, it's almost getting close to 90 degrees, right? And so that's what makes the rainbow happen. It's called dispersion. Different indices of refraction cause different bending for the different pieces of the light, the different rays of light that come in, each with its own wavelength, each with its own frequency, so each with its own amount of bend, and that's how we make rainbows.